The universe is dark and cold and empty. Everything that was once there has decayed away, and only the very few stable relics are left and make up our world today. But every single one of those particles knows what went on in the Big Bang because they took part in it. Even the vacuum knows about the laws of physics. And with giant accelerators and protons moving at very nearly the speed of light, we can recreate the conditions that were there right after the Big Bang and see what went on, this time with us as spectators, so that also we can understand the universe we inhabit. That is what I do, and I love it. But that is not how I usually introduce what I do at a casual dinner party. But our understanding of the universe comes from a marriage. In fact, a marriage between the science of the largest cosmology and the science of the smallest particle physics. Now, we physicists are a bit like gossip journalists, because it is a happy marriage, and we understand a lot of things about the universe. But we're not looking for the happiness in it. We're looking for the cracks. We're looking for the things we do not understand. And there are things in that marriage that we do not understand. Cosmology sees dark matter, dark energy, and particle physics have no explanation for that. And we continue as gossip journalists because we also want to see the flaws in each single character. And particle physics has come a long way and has many good explanations. Yet, that is also a flawed character. Because even though we have a super fine theory, we also have a prediction that any structure in the universe should never have been made, and all particles should be massless and hence moving at the speed of light. And that's not what we see. So we back down and say, all right, where did this problem come from and how do we solve it? It's 45 years ago we saw it, and I'll talk about the solution. So up here, you see, if we zoom in on matter, we get atoms. Atoms made up sort of the 20th century table of elements. And it's through atoms that we understood our world and all the chemistry and science we're doing. Now, we zoomed in further and found out there were electrons around a nucleus. That step took us to cell phones and computers. We also understood the nucleus in terms of protons and neutrons. That gave us power, and perhaps the power of the future, in fusion power. And we've zoomed in even more to get quarks. And so, the table of elements of the 21st century looks like up there. We have quarks and leptons with which we build our world, and on the other side we have forces. And in the middle, we have this elusive Higgs particle that I'll return to. But suffice to say, look up and see that, in fact, the old table of elements of the 20th century is made up of just 3 particles. With that, we can explain everything. Now, what are the laws of physics? What governs that? With the exception of gravity, which does not rule anything in the world of particles, we have a very, very good model of it. Here's the formula. Take a good look at it. In fact, don't. Take many years of education to understand what's going on up there. But that formula tells you anything about chemistry, material science, all your cell phones, any technology, the color of your skin, how the universe works. And believe me, that equation, you can ask it questions like, you have an electron, it spins, so it's a magnet. How much of a magnet? I asked the equation. In fact, we have people calculating it. And with 12 decimals, they can tell how much a magnet and electron should be. And then we go measuring it. And lo and behold, it matches to 12 decimals. And any experiment we can think of, it matches. Now, that precision corresponds to me standing here, playing golf, getting hole in one, not at the other end of the scene, but at a golf course in China. And I'm so accurate that I do not need the ball to bounce. No, it will hit straight into the hole without touching the edge. That's the precision. If I could do that in golf, you'd probably agree with me that I understood golf well. Right? And that's why we believe we understand much of the universe very well. However, that formula also tells us that no particle should have any mass and hence move at the speed of light. And that's just plain wrong. So what do you do with 40 years of science work and Nobel Prizes? Do you throw it all away, or do you try to think of an idea that might make up for this? Some missing piece in the puzzle. And the following is a movie to illustrate the idea of what we call the Higgs particle and the Higgs mechanism. So, imagine a field in the universe that the Higgs particle makes. And that field touches on particles which have a mass. So if you are a photon without mass, you will come along and you won't feel anything. You will just pass through at the speed of light. But now you have mass and you interact with a Higgs particle, and some of your movement is made into mass. Some of the energy from the movement is made into mass. Now that's what the Higgs particle does. For the 45 years that it's been missing, theorists have thought of at least 500 alternative theories to this. And we have no clue which one is the right one. We have no understanding. It's a missing piece. And it's so elusive. You need to take protons and smash them together at great energies, and afterwards try to see what went on in those collisions. And only 1 in 10,000 billion might create a Higgs boson if it exists. Formidable challenge? Oh yeah. And so it begins. Up here is a picture of CERN's Large Hadron Collider. It's a tunnel just outside Geneva, 27 kilometers in circumference. And down underneath is an accelerator. And you might think, how do you build an accelerator? Well, here's an illustration. You go to IKEA and you buy 60,000 of these. And as shown up there, you call IKEA before you make any black holes. And then you piece it together, pour protons in it, and next thing you know, you're on a flight to Stockholm for a fancy dinner with the royals. There you go. It's not that simple. I spoke to one of the accelerator scientists behind it, and he gave me a piece of the superconducting part, and it looked a bit like just a copper thread, 1 millimeter in diameter. And he said, well, inside there are 6,000 niobium titanium conductors. All right, how many companies can even make this? He said, 10. All right, one company must have been happy to have CERN sort of order in their store. And he smiled back and said they were all 10 happy because 9 of them were doing nothing but that for 5 years while the last company could pick up the rest of the business. And the LHC is full of things like that. So pay respect when we talk about the LHC, please. Now, we got an accelerator that can accelerate protons up to high speed. We collide them, and out of that energy, we might create a Higgs boson. But we need to be able to see what goes on in those collisions. And so we have to build cathedrals of science and technology underground. And it starts like this. A major cave, but eventually that cave is going to hold a wonder of technology, probably the most advanced we ever built. It ain't going to stay that way because technology is going to slide on and this is going to become old-fashioned at some point. But for now, this is it. And here are the numbers. There are 100 million things in that detector that can say, bing, I got hit by some particle. And we do so 40 million times a second, 25 million seconds a year. Now, the information, raw information out of that corresponds to all your cell phones, all your computers, all your telephones, all your network, everything in one go from the entire world, whang, at you. But we've come up with ways of taking out the 1 millionth part, putting it on computers. And we're not gigabytes or terabytes, it's petabytes. And we have used 100,000 computers in a grid to analyze this data, this amount of data, to get results. And we look through this data. And then just once in a while, an event like shown up here comes along. One that looks like the Higgs particle, and another comes along. And you gather with your colleagues, knowing that perhaps after 45 years, you might finally hold the answer. And believe me, the meetings that you sit in discussing how to present this are tense. And there are people who sat there for 25 years, spent all their research in obtaining exactly this. You're sitting with it. And people work night and day. And on the 4th of July this year, CERN could present the result that we had finally found the long-sought Higgs boson. And then I know that you're gonna ask, what can we use that for? And frankly, I don't think we'll ever use the Higgs boson for anything useful. Sorry. We're never gonna use the fact that the universe is 13.7 billion years old. But it's cool to know. It is cool. And. In the process of building these cathedrals of science and coordinating so many people who, by the way, aren't organized by one organization, well, CERN, but there's not a single boss that can say, you're fired because you're not doing your job. No, people work on what they want to work on. And this, simply, the common goal is what's driving it. And in the process of building this, CERN has invented the World Wide Web. And in some respects, the World Wide Web is a child of the hunt for the Higgs boson, which we can, by the way, not use for anything, but on the way, we sort of found something. And what now? What now? We have the Higgs. Well, I'm on to chase dark matter, dark energy, extra dimensions, whatnot. Of course, we finally got our toy. It's fantastic. And in this respect, physics is like sex. Sure, it may have a practical purpose, but that's not why we do it. Thank you very much.